Cosmic inflation, how the universe expanded faster than light. Cosmic inflation is a mind-bending theory that revolutionized our understanding of the universe's earliest moments. It proposes a period of incredibly rapid expansion in the first fraction of a second after the Big Bang. This expansion wasn't just fast, it was faster than the speed of light. Inflation is crucial for explaining many of the observed features of the cosmos. It addresses fundamental issues that the standard Big Bang model simply can't account for. It's a cornerstone of modern cosmology. At the heart of inflation lies the concept of the inflaton field. This hypothetical field permeated the early universe, possessing an incredibly high energy density. This energy density acted as a repulsive force, driving the universe's exponential expansion. Think of it like a period of supercooling, where the universe was in an unstable, high-energy state. It was poised to explode outward, driven by the energy stored within the inflaton field. This explosion is what we call inflation. This explosive expansion lasted for an unimaginably short period, from about 10 to the power of minus 36 to 10 to the power of minus 32 seconds. Yet this tiny fraction of a second had profound consequences for the entire universe. It shaped the cosmos we observe today. The universe expanded by a factor of at least 10 to the power of 26 during this brief inflationary epoch. That's like taking something the size of an atom and instantly expanding it to the size of our solar system. This rapid expansion smoothed out the universe and set the stage for the formation of galaxies and stars. One of the biggest mysteries inflation solves is the flatness problem. Observations show that the universe is remarkably flat, meaning its geometry is very close to Euclidean. This is a puzzle because without inflation, the initial curvature of the universe would have needed to be incredibly fine-tuned. Any deviation from perfect flatness in the early universe would have been amplified over time. The universe would have either collapsed in on itself or expanded so rapidly that no structures could have formed. Inflation provides a natural explanation for this observed flatness. Inflation stretched the universe dramatically, smoothing out any initial curvature. Imagine blowing up a balloon. As it expands, its surface appears flatter and flatter. Similarly, inflation flattened the geometry of the universe. Another major puzzle addressed by inflation is the horizon problem. The cosmic microwave background, CMB, the afterglow of the Big Bang, is remarkably uniform in temperature across the entire sky. This uniformity is puzzling because in the standard Big Bang model, many regions of the CMB were never in causal contact. These regions were so far apart that light, the fastest thing in the universe, would not have had time to travel between them since the Big Bang. So, how could they have reached the same temperature? Inflation provides a compelling solution. Inflation suggests that these regions were once in very close proximity before the inflationary epoch. They were able to interact and reach thermal equilibrium. The subsequent rapid expansion then separated them, but they retained their uniform temperature. Inflation also provides a mechanism for generating the seeds of structure in the universe. Quantum fluctuations in the inflaton field, tiny random variations, were amplified during inflation. These amplified fluctuations became the initial density variations in the early universe. These density variations, though small, were crucial. Gravity acted upon them, pulling in more and more matter. Over billions of years, these variations grew into the galaxies, stars, and planets we see today. Without inflation, it's difficult to explain the origin of these initial density variations. Inflation provides a natural and elegant explanation for how the universe went from a nearly uniform state to the complex structure we observe. It's the reason we're here. While inflation is a remarkably successful theory, the exact details are still being researched. The inflaton field itself remains hypothetical. We haven't directly detected it. However, the theory has been remarkably successful in explaining key observations about the universe. Inflation provides a compelling framework for understanding the early evolution of the cosmos. It continues to be a major area of research in cosmology. Scientists are actively working to test and refine the theory. Ongoing research includes detailed observations of the cosmic microwave background. Scientists are searching for specific patterns in the CMB that would provide further evidence for inflation. These patterns are subtle, but potentially detectable. Another key area of research is the search for gravitational waves generated during inflation. These gravitational waves would be a direct signature of the rapid expansion. Detecting them would provide strong confirmation of the theory. The search for these gravitational waves is a challenging but potentially groundbreaking endeavor. It requires incredibly sensitive detectors and sophisticated data analysis techniques. If detected, they would open a new window into the very early universe. By studying the CMB and searching for gravitational waves, scientists hope to further test and refine the theory of inflation. They aim to understand the nature of the inflaton field and the precise details of the inflationary epoch. This research will help us unravel the mysteries of the universe's origins. The future of inflation research is bright. With new telescopes and detectors coming online, we are poised to learn even more about the universe's earliest moments. The quest to understand cosmic inflation is a quest to understand our place in the cosmos.